Her research interests include numerical analysis, condense sensing, and regularization method for mathematical optimization problems. So she will deliver the second part of the tutorial. The floor to you.
Thank you very much. Thank you very much for this opportunity. So my lecture was very much prepared with together and with a working on a few different expert, but I became interested in this methods as alternative, conditional manifold as an alternative to solving constraint optimization problems. So I will make more general comments hopefully towards the end. And what I would like to do in my talk is to talk a little bit about, as I mentioned, gradient descent and the analysis of gradient descent on manifolds and gradient descent, just to give you a flavor of that, to contrast it with Euclidean approaches, and then I will move on to an application where we have used Riemannian formulations and nonlinear matrix completion, and that will hopefully give you a sense of what you can do with these tools, some analysis, some numerical results, and then I will try to draw some general conclusions. Okay, so let us recap a little bit from what you've seen in the previous hour. We minimize f of x, and x is, so we minimize f of x, and x belongs to a manifold. And we will see some examples of this later on. Basically, sometimes this function f is just defined on a manifold, and this manifold could be given by, think of it as a subset of, say, nonlinear equations, for example. But it's more specific than that. It has more geometric structures, as we will see. So just to recap, we are talking here only about the case when we view M as embedded into a vector space, into a Euclidean vector space. And at every point, we have at every point x, we have a tangent space, okay? And this is a linear subspace, linear approximation of the manifold, and it is low, okay? So that's the main difference. But I want you to think about it in a simple way that in this tangent space, I can do whatever I want, kind of thing, like whatever I can do in Euclidean space, I can do there. That's an easy way to think about it. But I only will have a local sense of what's going on, okay? Because it changes at every iteration. And then I have to have this mechanism that takes me back onto the manifold with this kind of retraction, okay? So I will have a retraction at any point, say S, and this retraction will take me from the tangent space into the manifold. Okay, so it allows me to be feasible. What else do we want to define? Well, we want to define a metric on the tangent space, an inner product, and so we define an inner product, a distance. So in the tangent space, we can use these tools to help us move, and then we use the retraction to come back onto the manifold. And importantly, we have this notion that Estelle introduced of gradient. Okay, so we can look at directional derivatives. So just to mention that the directional derivative, right, was defined through this retraction. So I want you to notice that the function f composed with the retraction, okay, this goes from the tangent space onto R. So this is the so-called pullback of my function. And the nice thing about it is that I want you to think that with this composition, I can do anything I want. I can do Euclidean things, okay, because it lies in the tangent space. Okay, yeah, that's the crucial thing. So that for this reason, for this pullback, I have the notion of directional derivative. There's no problem to define the directional derivative. This is what df on v is, right? Directional derivative, and applied to this composition essentially. And I can represent that in terms of inner product projections of my direction v onto this vector that will be my Riemannian gradient. Okay. And furthermore, what is very important in optimization is some notion of Taylor expansion. So again, this function, this pullback, this is my pullback here, I can talk about a Taylor expansion for it. The pullback at s equals 0 is just f of x. So this function agrees with f at the base point x, where I draw my tangent space. And then my Taylor expansion, I want you to notice that, of course, it's related to this inner product, the local one in my tangent space. So an inner product on the tangent space that's drawn at my point x. Okay? And then higher order term. So basically, you can say, oh, it just looks like a Taylor expansion. It is, except that I have a local metric here, and everything lies in this tangent space. I mean, in R, but it's related to the tangent. Okay, so with these tools, okay, so the Riemannian gradient lies in the tangent space. We are going to try to move down minus the Riemannian gradient as we would do in gradient descent. So let's also talk about optimality notions. This is a typically non-convex problem. And so we talk about the global minimum and the local minimum on the manifold. Right? So a point is the global, of course, if it takes the smallest value over all the points in the manifold, or locally, if it takes a small value in a neighborhood on the manifold. Okay, so only locally f may be minimized there, as is typical for non-convex problems. But here, even if f has some notion of convexity, the manifold is not convex, so you have this problem much more often. Right, so now, because global optimality is typically NP hard, what we can try to do is to find local solutions, and this is what these methods do. So how do we define stationarity? Well, one can make analogies to the Euclidean case, and lo and behold, you can say that the point is first order critical or a stationary point of my function f on the manifold if the Riemannian gradient is 0, okay, at that point. You can define it more typical of manifolds as composing f with for any curve, for any smooth curve on the manifold. If you compose f with that, the derivative of that univariate function, right, is 0 at the base point, at my base point x. Okay? So that point is then stationary, that's the basic definition. But then you can show that that's equivalent to the Riemannian gradient being 0. And basically, you can go some kind of the directional derivative to show that. So, of course, just having a 0 gradient, as in the Euclidean space, does not imply that you have a minimizer, right? In a non-convex case, I may have minimum, maximum saddle points that have 0 gradient. Okay? However, if I'm trying to decrease my function f and obtain a 0 gradient, hopefully that takes me towards the minimum. That's how we usually do it in Euclidean space as well. Okay, so here's the idea that Estelle presented. So let me go quite quickly through this. So I'm at a point escape on the manifold. I move onto the tangent space at that point, And there I take the negative Riemannian gradient and I move a certain fraction alpha k on it, which is a scalar, a positive scalar. Okay? I will talk about how to choose this alpha k, this learning rate, and then I project that point using a retraction back onto the manifold so that I stay physical. Okay, and then I repeat. Okay, so here it is. Again, this is just a you choose alpha k here, or you can choose it after you calculated your Riemannian gradient, so that you decrease f. So you could fix it, like is often done in machine learning, a fixed alpha. You could choose it to globally minimize with respect to alpha the pullback along the negative gradient direction. That would be corresponding to what's called an exact line section optimization. But this is too expensive. So this fixed step size is inefficient typically. The optimal step size is too expensive. So what you often do in practice is you start with some initial guess alpha 0, positive. You see that's the function, that's the pullback along for that value here, alpha equals alpha 0. Does it decrease compared to the value of f at xk? If that's the case, that's your correct alpha. Otherwise, you shrink it. You know, by the way, you know that the negative gradient, Riemannian gradient, is in such a way that if you move a sufficiently small distance along it, you are guaranteed to be able to decrease the function. So this property that's true for Euclidean gradients is also true for Riemannian gradients. So you know that there is a value of alpha such that you could decrease your function at a new point, yeah, compared to the value of f at xk. So the question is how to find that, and so you would typically just try to guess an initial value for it, and then keep shrinking it until you find a value of f lower than the f at xk. So that's a more practical way of calculating the learning rate. Okay, so in terms of limits and convergence, well, we have usual limits from in topological sense. Okay, so an analytical sense. So you can talk about accumulation points, limit points of a sequence of points on a manifold. Okay, if any neighborhood for every neighborhood of the limit point of a sequence of points on the manifold, there will be some value of k such that the sequence enters this neighborhood, and also accumulation point in similar way. So you have a subsequence that is convergent. Okay. So let us try to give a global convergence result for Riemannian gradient descent. So I have a function f on the manifold, okay, and it's bounded below, okay. It's bounded below on the manifold, because if it goes to minus infinity, there is nothing to prove, okay, for convergence. I assume that, so I apply Riemannian gradient descent. I haven't told you how I'm choosing the step size alpha k, the learning rate. So I apply Riemannian gradient descent, and this is my iterates xk are generated from that. And I assume that there exists a constant c such that the function from one iteration of Riemannian gradient descent to the next decreases by at least a multiple of the square of the Riemannian gradient measured in my local metric. Okay? With these properties alone, we can show then the Riemannian gradient goes to 0 in this local metric, but that can be shown under assumptions. We can show that then there are limit points, and that then this gradient at any limit point is actually 0. The Riemannian gradient is 0. So all limit points of the sequence of Riemannian gradient values at the iterates are critical points of our problem. Furthermore, we can give something called the global rate of convergence. Maybe you have heard of this. Many people often try to do no asymptotic rate, global rate of convergence. So in this case, what you can say is that you are guaranteed to be able to decrease your Riemannian gradient at the rate of 1 over square root of k, where k is your iteration count. Okay? So that means that this will go below any user-specified epsilon in number of iterations k proportional to 1 over epsilon squared. So it's a sublinear rate of convergence because this function f is non-convex. Right, so we'll talk a bit more about that, but basically this is essentially the same rate as the Euclidean gradient descent if you applied it to both constrained and unconstrained optimization problems. Okay, so it matches in order gradient descent. Okay, so just to show you that the proof is very easy, and because some of you maybe have to read optimization proofs from time to time, I thought this would be a useful exercise. So it's a usual telescopic argument. So what we look at is, we look at decrease in the function. So what I know, okay, so let me remind you what I know. I know that f at xk minus, I assume this, I haven't told you how I'm going to achieve this, is a constant times the Riemannian gradient at xk squared in the local metric. Okay? So what I have to do is, so I know that the function f, right, so this is positive, so the function f will go down by some amount. That's what I really need in an optimization, not just strictly. So now what I can do is I can look at the total decrease from where I start, okay, from where I start all the way to where I got to, but I can go everywhere. I mean, I can go far in my algorithm, right? For each one, I have some decrease, okay? So I can sum up all these decreases. So that will give me a bound on how much the function decreases from where I started to where I got to. So here I have a term, right? Will cancel with this. So all terms will cancel by this telescopic argument. And I'm left with fx0 minus fxk plus 1 greater or equal to c, and then sum of all these gradients, xk squared, xk, sorry, xi, let's put I here, I from 0 to k, right? But I know that I cannot keep decreasing my function forever because my function is bounded below. So I know that there is a bound here that doesn't depend on k, the lower bound of my function f. Okay, but this is true for all k. Let k go to infinity. Okay, let k go to infinity here. Why not? Nothing stops you. Put infinity here. Okay, so if k goes to infinity, but this is bounded, right? So I have a series that's convergent. I have a series that's convergent, right? Then that immediately I get that the terms of the sequence are such that they converge to 0. Okay, as I or k goes to infinity. Okay. So that's the, you've never taken an optimization course, that's your first few lectures. Okay, so there you are. So this is very similar to ingredients from the Euclidean space. Right. Okay, so convergence follows quite easily. Also a global rate. How could I deduce a global rate from the same argument? Okay. Well, I shouldn't go to limit. Okay, I shouldn't go to limit. So I'm going to drop this k here. All right, I'm going to put back my k. So what I know is that this here is greater or equal than C times K times the minimum value of this gradient at xi, okay, for I from 0 to k, right? Every term in this sum, I minorize it by the smallest value of this, of the same thing in that sum, right? Trivial. But that means that I immediately have a k here, right? Every term is minorized by that. I have k terms in this sum. Okay, plus 1, okay, 1. K plus 1, okay, this. Right, so this gives me from here to here that k plus 1 is less than or equal to fx0 minus f low over c, sorry, what am I doing? The other way around. The gradient, sorry, the minimum value of the gradient, okay, right, the norm of the Riemannian gradient squared, gradient fxi squared, okay, less than c over k plus 1. You want to put k here, just do k minus 1 here, and then do k here. Right. Okay, so if I go back to my value here, right, I told you is bound, okay, right? So I'm almost there. I dropped it, I have a square here, but minimum of positive square numbers is the same as just putting the square root here. Yeah? So what I'm guaranteed is that there will be a value from 0 to k of this Riemannian gradient, right? That is smaller than this. Okay? So if I want to make this less than epsilon, then I'm guaranteed to get that if this is less than epsilon, so I get the worst case bound, that k is, I put here less than epsilon, right? Then k is like 1 over epsilon squared. So the gradient is not monotonic, of course, and so we cannot guarantee that all the points will be like that, just that we will find one point where the gradient is small. Right? It may go back up. Yeah. In the end, it will be small because I also have convergence. But these I'm trying to do a global rate. Okay. Right. So that's my proof. But I've made a strong assumption. I've made an assumption that I have this decrease here, right? So how could I possibly achieve this kind of decrease? And this kind of decrease is all you need for Euclidean, Riemannian, all methods that involve gradient descent. In fact, many methods, you can only prove per iteration this kind of decrease. Okay, you can show that actually the gradient goes to 0, even though you just have this local metric, the true Riemannian gradient goes to 0. Okay, so let me go on to the case of how can I achieve this decrease. I need two ingredients, right? It's connecting function to gradients. So I need some form of smoothness. If the function is not smooth or smooth enough, I may not be able to relate how the function varies with how the gradient varies, right? So this comes from assuming some form of some sufficient smoothness in the function in the form of some kind of Lipschitz continuity of the gradient. Okay. Now we have a problem. Okay. So we, before I tell you about the problem, so we need Lipschitz some smoothness of F, and we also need to make sure that the step alpha, the learning rate, is good enough. Okay, so let's start with smoothness. Okay, so if I wanted to do, so I'm gonna maybe start. Let me go in order. Okay, I will explain to you why we assume this. This in a bit, but trust me. What I'm going to assume is a consequence of kind of Lipschitz continuity that you usually see it as a consequence. So we assume that the pullback, this composition of F that lies on the tangent space, of which I have Taylor extension and everything, is less than f of x. So I assume that f at Rxs is less than f at x plus so this is my Taylor expansion, okay? Plus L over 2 S squared. Okay. So I assume that the function satisfies this for some L here that is independent of x. So there exists a value here that doesn't depend on the local tangent space such that this property works. So this is a consequence of the gradient of the pullback being Lipschitz continuous. Okay? It's a consequence of that, but not the other way around. This is more general, so I can have this, but not necessarily have that the gradient of the pullback is Lipschitz continuous. But this is only, it's kind of specific to x equals 0. I'm kind of basing everything at x equals 0. So it's a more restricted property, not asking for everywhere in the space for me to be able to control these variations. Okay, so what do we do with this? So remember, S for me was minus alpha Riemannian gradient. Okay, that was my step. So if I let S be minus alpha Riemannian gradient, okay, I plug that into there, and it's going to tell me something about how much I can decrease F, right? What I will want to do is to let xk and get this to be like f at xk plus 1 and this to be like f at xk. And then I move it on the other side and I get a bound on my decrease in f. Okay? So this is what we do. So let's say s is minus alpha. My new iterate, of course, is just a retraction of that. I plug that in. Gradient times gradient inner product with gradient in x just gives me the norm. And then here I have alpha squared. Yeah. So I put that in. I put this quantity into there. And you can see that these two terms are the same. And you end up with this f at xk plus 1 by definition, right? That was my next iterate, is less than that. And then here is my constant C, okay? My constant C is this term, alpha 1 minus L alpha over 2, right? So with this, so I move it on the other side and I get my decrease, okay? Now, this is only really meaningful. I need C to be positive, right? If this is positive, so alpha has to be sufficiently small. And also I can think of what is the best alpha to use in here such that the constant C is as good as possible. Okay. So for that, I can maximize this simple function in alpha to find the best value of alpha. And when I do that, I find that alpha is 1 over L, where L was my smoothness constant from here. So then C is 1 over 2L. So these, for those of you that are familiar with Euclidean gradient descent, may be very mindful of those quantities. So here we have the convergence with a specified step size then. So if alpha k is 1 over L, I have global convergence of Riemannian gradient descent, and a global rate of convergence that matches in order the Euclidean case. Okay. So again, this tells me that if I want the gradient to be above epsilon, then the number of iterations is at least epsilon squared, okay, which is sublinear. Okay, and this doesn't depend on n. Okay, you have your tools that tell you how to calculate gradient, Riemannian gradient, and you're good to go. Okay, now in the usual Euclidean setting, so pause for a moment to think about the usual Euclidean case. In the usual Euclidean case, we would do Lipschitz gradient, right? The Lipschitz gradient of f would immediately imply for me this so-called overestimation property, okay? This, which is fundamental to convergence proofs of all optimization algorithms. So the difference is, you see that the metric for us is local, okay, and this is Riemannian instead of Euclidean gradient. This is just, Taylor. You use the right form of Taylor expansion of f in integral form, and you get this bound. So now, why didn't we just in our proofs? Why didn't we just use Lipschitz Riemannian gradient? What's the problem with that? So why can't I just take this Euclidean setting, put instead of grad f, put Riemannian grad f? What do you think?
You can't use your retractions anymore?
Yeah, and if I put the Riemannian gradient, then I have to put immediately the norm is not some Euclidean, it becomes x. Yeah, immediately I have a local measure here. Right? Immediately here, this norm has an x. So the gradient here is at x, so that's not a problem. But this Riemannian gradient is at the next base point, at say xk plus 1. But at xk plus 1, I have a different tangent space. So that's a problem. So what I need to do, I need to think, how can I transport vectors? How can I transport vectors from one point here with a different tangent space? I need to be able to move it onto this tangent space at xk, so I can measure my distance between them, yeah? That's the problem with Riemannian geometry. It's tricky. You can do it, it's called parallel transport. You can do that, but it's messy. Okay? So you can't, because this gradient would lie at xk plus 1 would lie in a different tangent space than this gradient at my base point. So that's the tricky bit. And that's why we proposed to use this overestimation form, okay? To use this overestimation form here, or to think of working with the slightly stronger notion of Lipschitz continuous gradient of this f hat function, okay? If you just say that, rather than the actual Riemannian gradient to be Lipschitz, you say, I just want the gradient of my pullback to be Lipschitz continuous. Okay, that's local, but assume that there is a constant L, that the local Lipschitz constant of my pullback is independent of x or bounded by some other constant L. Okay, then I have this property. So, for example, this is true if the manifold is compact. Okay, for example. Okay, but with this property here, or gradient of the pullback being Lipschitz, the analysis and the analogies to Euclidean case are very nice and very, you can match the same analysis, the same result, and it makes sense, and it's what, you would use it like this in practice anyway. Okay? Right. So, I have a lot more things to tell you, so let me get ahead a little bit. So I told you already, you can choose your line search, you can have an adaptive line search alpha, which in optimization we very much believe in. Machine learning doesn't believe in it, but we believe in it. It's very important to try to be adaptive with your alpha rather than a fixed value, because it will lead to short steps. Okay. We also have local convergence. Local convergence for first order methods means you assume somehow you got sufficiently close to a local minimizer on your manifold. And this local minimizer is nice. It has positive definite Riemannian second derivatives. So it's a true local minimizer, non-degenerate on the manifold. The rate, if you're sufficiently close to it, the rate of convergence of Riemannian gradient descent is then linear. Okay, so this matches Euclidean set. Okay, I will go ahead with that. You can find proofs of this. Okay, so this global rate of convergence that I presented, the very first paper that did global rates for non-convex optimization on manifolds is our paper in 2019. So we did Riemannian gradient descent with this kind of assumption, with various step size fixed or adaptive. And so if you want all the nitty-gritty details of these proofs and carefulness and everything, I recommend that paper. In that paper, we also do second-order truss region methods, where you look at what does this property become when you add not just Riemannian gradient, but Riemannian Hessian. And the complexity in that case, when you do global rates of convergence, it allows you to quantify not just getting close to a first order critical point on the manifold, but to a second order critical point on the manifold as well. However, the first order complexity of epsilon to -2 of this 1 over square root of k, that is just to first order criticality, is not optimal in the Euclidean setting. The optimal bound would be corresponding to a complexity of not epsilon to -2, but epsilon to -3 parts, which comes from the cubic regularization algorithm. And so we went on and generalized that bound of epsilon to -3 to manifolds, and it was a lot of work, because we tried to keep to very nice assumptions like this, and we had various difficulties in that context, also to do with parallel transport of vectors, because you don't just have consecutive gradients that live on different tangent spaces, but you also have consecutive steps and so on, so it's more complicated. But anyway, I recommend this paper for it. And Nicolas summarized some of these results in his more recent textbook. Okay, so let me tell you a little bit about an application of this, where I will touch upon truss region second order as well. So Estelle mentioned matrix recovery or matrix completion or recommender system. So somebody gives you a matrix and it has missing entries, and under the assumption that this matrix is low rank, you can actually recover it. I will briefly mention this, and then I will tell you what do we do when we don't have this low rank structure. Can we recover matrices with missing data? Okay. So first of all, what we care about is that we are going to see measurements of our matrix. So let me just set notation and say that I'm going to sense my matrix M that I don't know. Okay, either I have so-called entry sensing, so I know specific entries in the matrix, like your preferences for films or something, right? So I would know those entries for you and your friend or something. Or I can measure them through some, if they are signals or something like this, I can measure them through some Fourier transform, okay? So, of course, if somebody gives you a carload of measurements, you can do anything you want. But this is not what we are after here. We are after the case where we do not have enough measurements, okay? So we want to recover N from as few measurements, as few information as we can. So we want N to be less than N times S. N is a matrix that's M and X will be, okay, so N will be N times S, okay? So I want my number of measurements to be less than n times s, the number of entries in the matrix. Okay. So what I assume is that I have some either entry sensing, like I said, so AI is chosen to give me certain entries, or I have some randomized Fourier, for example. So I'm not doing full Fourier matrices because I'm trying to undersample. So I'm going to take, for example, random rows of Fourier transforms. So I will measure M through those, and then I will get some kind of linear inequalities for my measurements. Okay. And I can measure them for the inner product, for matrices, as is often common, we use the trace inner product. Okay, so low rank matrix recovery that Estelle mentioned will try to complete these missing entries, okay, but from undersampling, but assuming this assumption that the function that the matrix M is low rank. And sometimes low rank R, and sometimes you assume you know R. Of course, you need to have, when you have more columns than row, you need to be a little bit careful. Okay, there is a minimal limit of measurements that you need, which is n times r essentially, or n plus n times r, so that where r is the rank, so to be able to get anything. Okay, but that is not n times s. Okay, and so. Can be guaranteed to recover. So this was a big breakthrough, right? Like Rosteva was mentioning quite a few years ago now. How many measurements N do you need to recover? And you need something like S times R, where R is the low rank. Okay? So that's how many measurements you need to be able to recover your true M. But this is under the assumption that M is low rank. Now, in many applications, okay, so how do we, let me briefly, because it's related to what I'm going to say next, how do you find your low rank matrix? Here's where all these geometric approaches come in. You can minimize the rank of some matrix X subject to the measurement. So I bundle all those AI matrices into a big operator A, everything's linear. Now, the rank constraint is quite a difficult constraint, so we may replace it by minimizing the sum of the singular values of X. Okay, the so-called Shelton norm. But what people do is something else, is so-called Bourret-Monteiro approach, where X can be written as a product of, as a low rank matrix, by being as a product of U and V, both low rank. Right? So if, for example, if R is 1 and U is a vector, right? There is vector is U vector times V transpose vector. So that's a rank 1 matrix. Okay. So similar. So this is a very powerful nonlinear change of variables that is very much used. Okay, so you can do that, okay, and there are many papers that show this problem has a nice properties that local minimizers are global, though it's non-convex. But you can also have a Riemannian geometry approach to this, okay. So what we say in this Riemannian approach is, I'm looking to find X, and I'm looking to find the subspace on which it lies. Right? So I'm saying X is low rank, rank R. So find me the subspace U on which, of dimension R, on which it lies. Yeah. So I'm trying to minimize this gap between X and this projection on U. Okay. But I can think of it more nicely, where U is in fact the manifold of all linear subspaces of rank R. So that's the Grassmann. And I have linear measurements, all right? So I'm trying to solve this problem where I need to find both X and U. How do I do it? Well, I can find a matrix U that's orthogonal, or orthonormal, and with orthonormal columns, and the span of U spans the Grassmannian manifold. So I'm looking to find such a U representative from U, from the Grassmannian manifold, and to find X at the same time. Okay, so this is also used in this case, and what you end up doing is that to calculate this, for U, you just do an SVD for X and take the leading R. Okay. So now, then we get to what we try to do. So this low rank matrix completion, this is anyway very good for your culture to know. Okay? It's a very well developed field with connections with a lot of different areas. But there are cases where the matrix M has high rank, and you would still try to recover. Well, low rank matrix completion is not going to work out. It's just not going to work out. So what could we do in this case? So if the matrix is high rank, what can we do? Well, we can only really do something if this matrix is low rank in a bigger space somehow. So is it the case that if I lift the column, the points in this matrix, the columns of this matrix, a higher dimensional space, does the matrix M there look low rank? So this is what's called nonlinear matrix recovery. So it applies very much to union of subspaces models, to clustering, as I will hope to show in a moment. Okay, so how do we do this? Well, we lift it to a space of features, okay? So we take our matrix M that has S columns, so we take the columns, okay, that lie in Rn, and with this feature map, they may lie on a subspace in a much higher dimensional space Rn. If that's the case, I can essentially apply low rank matrix recovery in this higher dimensional space and recover my matrix. So this is the framework of nonlinear matrix completion. And we will see that it applies to a few things. Right? So phi is my feature map. Okay. Okay. So let me tell you that then, okay, so all I do then, where phi is my feature map, so that on the left column was my linear low rank matrix recovery when M is just low rank as it is, okay? With the Riemannian formulation, what we proposed here was to do that, but of course X becomes phi of X. Phi of X is my feature map, yeah, like that. Right, so now my problem, okay, is tricky because this objective function with phi can be very nonlinear. Right? So this is now not just because of all these constraints, but because of this will be a non-convex objective. Okay. So now the question is, what is phi? Of course, I need to specify the feature map and try to get some low rankness in that. Okay. Well. Before that, let me just tell you that, of course, it's connected to kernels. My feature map will take me to R big N, which I don't like. So to save on this blow up in dimensionality, I can use a kernel. So I can express my feature map with the use of a kernel. Okay. So I may try to represent phi with a kernel tree. Okay. So we can try to do that for every one of the features that I'm presenting. You can do that, feature maps. Okay. So just quickly, for some of you that work more with algebraic varieties, as I know some people here do. So what we can say is that assume that my matrix X or M, okay, lies on some on a system of polynomial equations. Okay, so if my given matrix M satisfies a system, a finite system of polynomial equations, okay, we'll see that this can look low rank in high dimensions. Okay, so then my feature map will be the matrix of all monomials associated. What I don't know here is I don't know to what degree of the polynomials should I lift my columns. Okay, so I don't know. So I'm given this matrix and the columns of it, and I'm saying that this column satisfies an equation like this, and the other column and the other column. Okay, so for every column I have a polynomial equation. Right. Now I could say, okay, maybe it's linear, maybe it's degree 2, maybe it's degree 3. I don't know what the D is. Okay? But that is one potential way to lift this up, to say it's lying on an algebraic variety. Okay, the simplest case here of that is union of subspaces model. So in this case, I only have essentially zero order monomials and first order monomials, and I have a bunch of subspaces. Okay, and so what I'm saying is that I know that my points, the columns of my matrix X or M, lie in this. So I'm imposing that in the union of these subspaces, not the intersection, the union. So I can write my problem as this product of linear hyperplanes. Okay? The product has to be 0. So each point lies at least on one of these subspaces. Okay, this is not a low rank model. Okay, if I try to recover these points in a low rank model, this will not work. Okay, so for the monomial lifting, you know, we have, dependent on the degree D of the monomials that we use, the feature space is combinatorially large. So this is not great. We can connect, there are results that connect the rank of these to my data and so on. So there's a lot of details that I won't have time to present very much. But let me ask you a question. Yeah.
Can you go back on the slide? What's that like dot D?
It's the componentized product. So I have to. It's the componentized product. I make everything into a vector. I take everything and make it into a vector, and then I make the product. It's connected to what Stella was saying. Okay. So you may ask, wait a minute. You are telling me that you have low rank in this union of subspaces, in this feature space. So here's a plot of the singular values of the kernel of the monomial features. Okay? And what you see is that you have this drop. Okay? You have various eigenvalues here. Okay? So the rank should be the whole dimension. This dimension should be like 100, but then you have that's S. Sorry. So yeah. So and you are in R10. And so the rank here will be like 26. So you have 26 large singular values, and then you have a big drop, and the rest of them are to machine precision. So we don't necessarily say, oh, it's going to be precisely 26 rank, but it's going to have a big drop. So it does have numerical small rank. Gaussian kernel for clustering. The Gaussian kernel will also give rise to a feature map, and you can see that when 2 points in a cluster are close together, this kernel value will be close to 1, otherwise close to 0. Okay, so that's how it is. So in a cluster, so if you see the kernel matrix, then you look at where there are the ones that kind of dictates your cluster. So the rank of this kernel will give you essentially the number of clusters that you have in some given cloud of points. Okay, this kernel is not quite so nicely low rank as the monomial kernel. So what we see is that you know these are the leading eigenvalues. This is what we expect for the rank, but actually, you know, the singular values of the Gaussian kernel are more slowly decreasing. Okay. So we can see, okay, we can overestimate here a little bit the rank, but there is, but you know, we do have a few more than what we expect. Yeah.
What is in the line?
Sorry. So here, this is the flow we care about. This is the number of singular values, the singular values of my Gaussian kernel applied to this data. So in the left-hand side corner, I have my X matrix or my M matrix that has all these. The columns of it are the points in this cluster. Okay. So I take the points in these clusters that are these dots here, and then I form this matrix X, and then I calculate the Gaussian kernel for it, matrix, and then I do the SVD of that matrix and get the singular values. And what I would love to see low rank, I would love to see that there is some kind of big drop after 2 or 3 singular values because there are 2 clusters. I don't quite see that. There is a drop here. There is a drop. There is a drop after 2. There is a drop, but there is also a lot more going on after. So this is only approximately low rank, but we can still, you will see that we can still do that. And then I do the same thing on the next picture with the 10 clusters. Same thing. I put all the points in X, and then I calculate the singular values. So again, I see that after 10, I have a drop, but it's not a drop to machine precision, okay? But I have a drop, okay? So I just have to be good in my numerics. Okay, any more questions? Right, so let me tell you how we use Riemannian. So the first approach is what I told you before. This is my feature. We can do it with kernels, but for simplicity, let me just put in the feature map. So this is my feature map. So it could be the monomial generated feature map or the Gaussian one or other things, whatever you have that you think may help here. And so I'm trying to find the subspace on which my data lies through this feature map, on which phi of x lies. So not x is low rank, but phi of x, I assume is low rank. Phi of x lies in subspace of dimension U, in a subspace U of dimension R. Okay. So my manifold is now cross product between a linear subspace and my Grassmannian. U, this subspace that I want to find, is that relates to big N, to my feature. So I look at the Grassmannian in that space. So rank R, and so N times R, big N. Okay. So what I will do on this problem, so I will treat this linear, this Euclidean affine subspace as a Euclidean, as a simple manifold, as a trivial manifold, right? It will coincide with the and then here I will do the Riemannian approach, but I can work with both of them together at the same time. This is more trivial than the other. Okay. I also can do second order. So instead of having just the Riemannian gradient like before, I will have a Riemannian Hessian also defined through directional derivatives. Okay, so I don't want to bother you with all the details. The part where, so X is to do with my linear subspace of measurement, and U is to do with how I'm trying to project phi of X onto this low-dimensional subspace. Okay? So I'm trying to find X and U. I can think of how I project onto A, that's trivial. I have to project onto null space. I have to find the basis of the null space, do QR on A, and we find it. Then you have to deal with U, and there I'm going to use my Riemannian approach for the Grassmann manifold. I can write down the tangent space, the projection of it, and basically I have to find a matrix U with orthonormal columns of rank R that spans my Grassmannian, and the range, basically I find that the tangent space is just the range of the new complement, okay? And this way I can calculate all the things I need. I have all the tools to calculate my projections onto the tangent space of Grassmannian, to calculate my Riemannian gradient and Hessian. So basically what we do is the retraction for the linear part is just the identity, and for the Grassmannian we are going to do the cheapest thing, which is QR. So when we time step, when we do our iterations in U, okay, we are going to do QR for that to get my retraction. Okay, so I take Q in QR to be my my retraction, to project me back onto my Grassmannian. So what we contrasted was Riemannian gradient descent with Riemannian truss region. Gradient descent is what I introduced earlier. Riemannian truss region is replace your line search with another form of safeguarding your iterates for truss region and use second order information. So you have to use some at least partial the second derivative. And here's time versus norm of the gradient for some example. And what we see is that first order is very bad, second order is very good. Okay. This is because, let me just say this as an optimizer, first order methods very much inherit the ill conditioning of your problem. If your problem has even milder conditions, you will not be able to get very far, and you will not be able to get high accuracy. So this is true whether you are Riemannian or Euclidean or anything. Okay, it's a general thing. You have to precondition first order methods to get away from ill conditioning of your problem. So, okay, so I need to stop soon, isn't it? Okay, so I won't describe truss region to you and Riemannian truss region. That is in the paper with Beaumont that I mentioned earlier. We have complexity results for it that characterize not only stationary points in epsilon -2 iterations like before, but also points that have small gradient and almost positive semi-definite fashion. And we have global rates for that. We also have an approach that does alternating minimization. So in this case, we see that in our problem, we wanted to find x and we wanted to find u. Yeah. These are two different blocks of variables. X was kind of easy because I have just linear constraints, and u was harder because I was on the manifold. Okay. So what if I treat them separately? What if I solve for x, my problem, okay? So fix u, fix the subspace you're in, and just find a better x to project orthogonally project phi of x onto this given u, satisfy your measurements, find that point, then fixing that in here, find your u on the grass manifold. Okay. So now what you do for this second problem, you're going to do SVD of phi xk plus 1, take the leading left eigenspace for that. Okay, as your guess. Okay, numerics, and I'm done. So we have this alternating minimization, convergence for it, etc. So here are some comparisons. So in both of these approaches, we use Riemannian optimization. So here we compare on algebraic varieties recovery. So here are iterations versus norm of the gradient in the first plot. And we see that the Riemannian truss region that does not do separate minimization, but together of the variables x and u, that's much better because of curvature information. In terms of gradient norms, this variant is much cheaper, so it does much better than using more information. Here we have gradient poles. Okay, again, the truss region beats it very much. And in terms of time, though, when we get to time, so when we look at accuracy and evaluations and iterations, basically the Riemannian truss region with both first and second order information is very, very strong, very high accuracy, as we expect from the Newton time method. When we get to time, though, that's when this alternating minimization starts to win. So this plot here, you see that in blue and yellow, we have this alternating minimization that's much cheaper per iteration, and they do better than doing Riemannian. So it depends what constraints you want in your application. So I will stop here. I recommend these papers in the slides. And I want to conclude by saying that I hope this application illustrates some of the power of the Riemannian optimization concepts that we saw earlier and how you can use them in application. I want to recommend as software packages if you don't want to implement, because you don't want to go and have to implement retractions necessarily. So besides Manoff, which is Nicolas MATLAB package, there is a package of Mario Lexano called GeoTorch, which does everything in PyTorch and has a lot of these algorithms implemented. If you just Google GeoTorch, you will find it. So depending on your uses, you can do so. This software comes with this geometric mechanism already hard coded. So if you're on one of these well-established manifolds, you can easily use them. Okay, thank you for your attention.